Okay, any other questions before we get started?
Will you read off that URL?
garop.io/dex/data-structures. And so you can go ahead, like you can breeze through these slides if you want, but we're going to talk more about them and go a little bit more in depth. They're not like fully comprehensive about each data structure that we're going to go over, but yeah. Okay, am I good to go? Okay, let's get this full screen. Okay, so let's just start with array and array list. So we talk about arrays. Arrays are a contiguous data structure. That means that when we go into create an array, it says, oh, I'm going to take up this amount of room and all in memory, and all of that is right next to each other. What's great about this is it makes it really fast and simple, because it says, okay, if I have element number 0, or in position 0 here, 1, 2, 3, 4, I can quickly go between each of them. If they were separated, it would take more time simply because they are literally separated from each other. Arrays are all right next to each other. I'm not going to go too much into arrays right now because I think that you guys have learned what arrays are, both in this class and in the intro to programming class, but does anyone have any questions about arrays that I didn't really think so. They're also really, someone has them. They're also really good. It's really good to know about them for interview questions. I think on HackerRank, if you do like their interview practice kit or whatever, it says that like 70% of interviewers ask about arrays. So knowing how to reverse an array in place, or just knowing how to do pretty much anything with an array using whatever language is really, really important. And the great thing about arrays is that they're pretty much the same in every language. Like JavaScript's a little weird because JavaScript likes to do things weird. But as far as structured languages like C#, they're pretty much the same. Okay, and then an array list. Who's here coming from CS142? Okay, so this is kind of like a vector in C++. They're unstructured, and so they don't need a specific data type. So like with an array in C# you need to specify that this array is of like type strings or whatever. But with an array list you don't have to, and they're flexible. So they grow in size, but they're going to double in size each time. And so that makes it really inconvenient if you only need one extra thing or one extra element, but it's going to grow way more than that. So it's going to be inefficient in that sense. Also, because they are unstructured, you have to keep track of what type each element is in it, which can make it kind of hard. So if you start putting a string in an int and you could put a dictionary in there, you could put another array list as an element in it. That you're going to have to make sure to properly validate which data type it is when you're pulling stuff out of it. So array lists are cool because they're more flexible, but at the same time you can run into issues with them really fast.
So I'm just trying to understand. It's like the array list. I create an array list and it automatically hashes out like 4 spaces for it.
Yeah, I don't remember how many exactly it does at the beginning, but then once that's filled up, it doubles in size, so it'll go to like 8.
And when you say it doubles, like it probably go like there, or it jumps somewhere else and doubles, or how?
I'm gonna guess. I don't know for sure, but I'm gonna guess that it will move somewhere else, simply because there's probably gonna be other things that are taking up that space in memory, so it'll jump somewhere else to double in size. Okay, and that's pretty much what you'd be doing with an array if you kept making it bigger and kept moving things around. Do you have a question?
It's not contiguous, right?
I think that they are. That's why it doubles, and like that's why. I wish I had that on hand, but we can look that. Okay, that's what I thought. Okay, sorry. Anything else? Any other questions? Let's talk about lists and double linked lists. So in C#, they just call it a list. Everywhere, like if you try to look it up online, you're going to find that this is actually a linked list, singularly linked list. So they're flexible, and this is because they are not contiguous. So that means that they have pointers that point to the next node in it. So let me talk about what a node is. So if we look at this image, are the lights? I don't know. Let's go.
It's the top one. Yeah.
There. Is that better? Sorry about that. So with a linked list, you have a node. It's basically a list of nodes, and what a node is it has data and it has something that's pointing to the next node in the list. So this data is whatever you specify your data type as for the list, and then it's just pointing. So if I have, so with a list, I could have one node be right here, and then like I can start it and just have one node in my list. And then a whole bunch of stuff happens in my code, and there's more memory allocated to those things. And then I say, oh, I need to add something to this list. Well, way over here, it's going to say, okay, this is where the next node is. And then the first node will receive the memory address of that next node so that it knows, hey, if you need to go to the next one after me, I'm pointing you over there. So CS142s, there's all this stuff about like pointers and everything. They're really useful though, and like that's what's happening behind the scenes with a lot of things. So that's how a linked list is working. They're structured in the sense that you have to specify their data type, at least in C#, and they're only one direction. So you can't, like the second element in a list doesn't know where it came from, but the first element, but it does know where it's going to go. Does that make sense?
Does it also have reference to what number it is in the list?
I'm not sure about that. I think it would depend on the implementation. I don't know if in C# if it knows exactly where it is. I don't think it does.
I wasn't sure if it would actually, but
Yeah. When I was looking through the methods before in C#, it doesn't look like it does, but you could make a function that says, oh, count where it goes. So a problem with this kind of structure is that if you want to search for something, so say we're trying to get to D, it can't just jump to D. With an array, you can say like your array bracket 4, and it goes exactly to that location in memory every time. With a list, it has to start at the beginning and go through each node in order to get to what you're looking for. Does that make sense? So they're going to be less efficient than an array, but still useful if you need something that's a little bit more flexible than an array. Okay? With a double linked list, yeah. Or any other questions about just a singularly linked list? Okay.
Sorry, I have another question.
Yeah.
Okay, so the array and array list are
Contiguous.
right? So that means that I allocate this much memory and that's what I get.
Yep.
Right? And then, but if I want to add to it, how does it know? Like if I want to add to my array list, how do I know where that's at?
Like in memory.
Yeah.
Stuff like C#, it'll keep track of all that for you, so you don't have to worry about it. Just know that it's going and it's allocating new memory.
Okay.
Is that?
So it still somehow points to it though?
Yeah.
Okay. So in that, like, at that moment, it wouldn't be contiguous, or how does that?
So the variable will just point to a new location in memory.
Okay.
So like if you call your variable A or whatever, or A list, then that variable will point to where your array list is now stored in memory. It'll stop pointing at where it originally was. So your array list is still contiguous, but where the variable is actually pointing to has changed.
Okay.
So you said these are like nodes, but these are not nodes?
These are nodes.
They are nodes.
Yeah. So when we talk about these, for lists, these are nodes. For a double linked list, this is a node. They're still nodes, but each data structures that have nodes, they're going to be a little bit different from each other. Okay. We'll get to double linked lists in just 1 second, and I'll talk about that.
Are you going to post these slides?
Yeah, they're on. I'll post them. They're on my GitHub page thing. Okay. Okay. So a double linked list. very similar to a linked list, except for each node also points back to where it came from. Oh,
And you said the linked list is just like the normal list.
yeah, that's a list in. But if you ever want to search for more about like a single linked list, that it's the same thing as it's the same structure. Okay, it's just weird because they didn't name it that. So double linked list, same. They still have nodes, but these nodes point to the next element in the linked list, and they also point back. So they're going to take up a little bit more just because you have to keep that data with it, but it's really useful because you can go back and forth. So an implementation of something like this could be like an undo redo feature on an app or like anything that you use, where when you undo something, you just go back, but then you want to maintain what you like if you wanted to go back forward. So then you can go forward again. Does that make sense? With both of these, you have this head that just points to the first node in the list, or like the list or the double linked list, and then your last element will just point to null. So if you insert something at the end, it'll create a node. The last element will then be pointed to that new node, and that new node will point to null. Any questions there?
So you point to null twice on the double linked list?
Yeah, so you're going to have the first element is going to point, its previous node is going to point to null, and then its last node is going to point to null. So because with a double linked list, like if you want to insert something at the very beginning, then you create a new node. That new node is going to have 3 parts to it: the data part, the previous part, and the next part. The previous and next are just pointing to the previous and next nodes. That new node, the previous is going to point to null, just like this one, and then the next will point to A if we're inserting at the front. And then we have to make sure that A then points its previous pointer to the new node we just created. There's lots of visualizations out there, like little animations on how to do this. I wish I should have put something in here. But that's a little bit more in-depth than I think Dr. Anderson went into about like how double linked lists are cool.
And what's the collection for a double linked list in C#?
I think it's just linked list.
Just linked list?
Yeah, so there's list and there's linked list, which I'm like, I don't know why they did that, because I don't know. Okay. Anyway, these are going to be faster at insertion and deletion. You're going to have efficient reorganization, but they're going to be slower iterating through it. Okay. Any questions about lists? Okay. Is this helpful so far? Okay. Okay, let's talk about stacks. And so I thought that it would be kind of helpful if we saw what something in C# looked like, and then also what something in JavaScript looked like. Just because I think it's helpful to see other languages and how implementations of these things get used. So what's really nice in C# is that we have, they have a stack in it, a stack data structure already like implemented, and so we can just use that. And if you remember, stacks are LIFO. So last in, first out, which means like his plate example, if you go to a buffet, you grab a plate and then it pops up more, and it keeps moving up until you can get to the bottom. Stacks are going to have methods like push. You can push things on. You can peek to look at the last thing that was put on the stack. You can pop the last thing off. You can check if something you can check if it contains something. So like here we can check if my stack contains Squirtle. We can clear it to get rid of everything, and then it also has a count property. What I would assume from this count property is that it's you should notice that it's a property and not a method. If it was a method, that would mean that they're going to do some sort of for loop to go through every single element in the stack and count and like have a counter that adds 1 for each thing. That can get really efficient if you have like 10,000 things if you're running a method that goes through all of that. So what they do is they just, as part of their push and pop method, they already have the counter as a property or as an attribute. and then they just add or subtract from it. So then you can get count really fast without having to go through the entire list. With something like JavaScript, there are languages like JavaScript that they do not have a stack implementation. However, what people normally will do is they'll just use an array, because arrays in JavaScript are super flexible, and you can just tell them to do whatever you want, and you can treat it like a stack if that's the kind of structure that you need. If you don't need a stack, don't use a stack. Like, you have to think about, how am I going to use this data? Is it necessary? So one of the great examples that Dr. Anderson used was the program stack, or the function stack, or whatever, where when you call a function, if that function calls a function inside of it, that gets added to the stack. That gets evaluated before finishing the original function. You can keep going higher and higher and higher, but whatever's on top is the thing that's going to be evaluated first. Does that make sense? Okay. Does anyone have any questions about stacks?
I know just like on the homework it says, for next week, it says like delete any item.
Mm-hmm.
I don't know if exactly what I meant by that, but in a stack you couldn't just like search for a certain item and then delete it, right? You just have to delete the top item loss.
Yeah, if you wanted to search for a specific item, how do you think you could do it?
Well, you can do like contains to see if it's there,
Mm-hmm.
but as far as like deleting an item, you just have to unload the whole stack, right, to delete that.
Yep, so one thing that you could do is you could make a second stack, pop everything off of that first one until you get to the element that you were looking for to remove, and then push everything back from that second stack, that temporary stack that you used. Does that make sense?
Yeah.
So when we're saying that, it's with removing an item, you still need to use the methods that a stack uses, but how would you implement that kind of thing? And that's one solution, is to use a second stack and then just pop it all off and then push them back on. Okay, let's move on to queues. I figure, is it okay that I'm gonna kind of going quicker through this stuff right now? Okay. Queues, they're pretty much the same. It's just FIFO instead of LIFO. So you have NQ, peak, DQ. You can check if it contains, very, very similar to a stack. JavaScript, you can do the same kind of thing. It's just where you end up looking at it in the array. Something that I forgot to put in here. Has anyone heard of a deck? Okay, so decks it's like a combination of a stack and a queue, where it can, it basically has it has all the properties of a stack where you can push and pop things off. It also has the same properties as same properties and methods as a queue, where you can NQ and TQ. So you can kind of go from both ways. Really similar to a linked list, in my opinion. But decks, I don't think I've ever heard anyone talk about any interview questions about a deck. So, but know that they exist. Okay, any question on queues? Okay. So dictionaries, really quick, I think that he talked about dictionaries a whole bunch. Key value pairs, I think that's the best way to think about it. It's just a collection of key value pairs. And so you can add them in, you can check if it contains a certain key, you can check if it contains a value, remove based on a key, and you can get the count of it as well. Same thing in something like JavaScript. You have to do it a little bit differently, but you can still do it. I kind of wish that I also had Python on there just for you guys to see like how different languages, like really see in comparison how different languages use these data structures, because the fact is that now that you've learned them, you can go and use them in like any language that you use. Go for it.
I was just going to say, is the dictionary the same as a map?
In most cases, yes. Yeah, there's even a map implementation in JavaScript. I don't know about C#, but everyone just uses objects. So if you're coming from iOS 3.03, think of dictionaries as objects in JavaScript, like that you can create just with curly braces. Okay, any questions? Okay, so which one should I use? This is like the worst question ever. But I kind of want to do a quick example. So could I have like 5 volunteers? Okay, come on up. Just come on up until we have 5. Okay, so go ahead. Do we have one more? Okay, so okay, so you guys just stand right there for now. So let's say right now that they are a let's implement a let's do a stack. So you push in, now you, and you, and you. So okay. Okay, good. So now if I want to get to element number, and this is 0-base element number 3, who's that?
It's me.
That's you. Okay. So how do I get there? Pop, pop, pop. What's your name?
Caleb.
Caleb. Cool. So we got to Caleb. But look at what we had to do. We had to go through 3 other elements just to get to Caleb. Okay, now you guys go back. Okay. Now pretend you guys are a dictionary. Each of you is the same element number that you were before, or position number, as your key, but your name is the value, okay? So if I say, okay, if I say my dictionary and say 2, and then you say, okay. So right there, all I had to do was say, which key am I looking for, and it immediately responds. So there's situations where this is going to be much more useful. You guys can sit down now. Where this is going to be much more useful. Where you have a dictionary that can immediately respond to the key that you ask it for and give it the value. But then if you use a stack, you can't just say, oh, I want element number 3. You have to pop everything off before that to get to that element. So the answer to this question it's the worst answer ever, it depends. Because it really depends on what you're trying to implement. And I think in your assignment, so you're basically trying to figure out how long it takes to do these, to do a removal in a stack, to do a removal in a queue. That's kind of the assignment, right? If you have the stopwatch thing, where you start it, you do something, and then you end it, and then you see how long it took. And so you can see right there, the stack takes longer. The dictionary goes a lot faster. A queue is going to probably take the same amount of time as a dictionary if we're looking for a specific element. But something like a queue is going to be the purpose is going to be a lot better for something like a print queue, where you need it to be ordered by what came in first. I wouldn't use a dictionary for a print queue because I need it to be ordered. And there's different reasons to implement stack, kind of like the function callbacks that we were talking about earlier. I hope that kind of helps to see why you would use different data structures and their use, because yeah. Does anyone have any questions, or did that help clarify at least a little bit more about how you might use different ones? Okay. Okay. Go for it.
Sorry, I have all these questions, but so if I'm iterating through something, a queue would be faster than a dictionary.
Well, it depends on what the purpose of, what you're doing with it.
If I'm deleting each item.
Those would probably be about the same, I think. If you're deleting each item, you can just use a lot of times you just use the clear function, and behind the scenes, it's probably going to do a for this and that.
Okay.
So I mean, it would still be pretty much the same because they'd have to loop through everything. Okay. Hopefully that was helpful. We're going to get on to more new stuff now, but I wanted to give you a good review of what was going on there. Okay, let's talk about recursion. Who's done anything with recursion before? Okay. you guys, I'm definitely not the expert in this stuff, so if you guys are like, hey, you're saying something wrong, just call me out. But I think that no matter what, I want to get you guys exposed to this. So with recursion, recursion is kind of like a method calling itself over and over again until a condition is fulfilled. Iteration is a loop repeatedly executing a block of code until a condition is fulfilled. So we've already seen things like for loops where, and you guys know what those are, for loops, while loops. You just keep going through. For loop is great if you know exactly how many times you need to go through it. A while loop is just until that condition is met. But with recursion, it's when you actually call yourself over and over and over again. So a great example of recursion is vectorials. So let's look at the iterative one first because that's what you guys are used to. So this is a function, factorial iteration. It takes in a number. We just have the result be number, because it doesn't really matter. And then we do this for loop. We start at the top. Actually, we start one below whatever our number is. We keep decrementing, and we keep doing result times I equals 0, or result times I equals result kind of thing. And then we're going to return result. So if we have 5, this is going to do 5 times 4 times 3 times 2 times 1 to get our factorial, right? Now we can also do this recursively. And with a recursive function, it would look something like this, where we take in the number. If number equals 1, we're just going to return 1. If the number doesn't equal 1, we're going to return this number times, and then we're calling the same exact function again. When we're calling this function, it's so say it's 5 again. So we're returning 5 times whatever the result of factorial recursion times number minus 1, so that's 4. So we're going to call this again, but number is going to be 4. And then as we keep going here, I'm going to draw this. So let's have number equals 5, okay? So this is like the first iteration. And we know that this is going to return, it's going to return number, let's call this 1, times number 2. That's basically what we're saying with when we're talking about this factorial recursion. This is what we're going to return. But in the second iteration of it, number 2 is going to equal 4, right? So now, and then we're going to say number 2 times number 3, right? So because this, as we see in our function, if it doesn't equal 1, we're going to keep returning something that involves the next number. Let me just draw this out. So number 3 equals 3. And so then we're going to return number 3 times number 4. Is 2. Sorry, number 4 times number 5. And then over here for our fifth iteration, number 5 equals 1. Here we're just returning 1. Okay? So we know that we're returning 1 here. So this is what number 5 is equal to. Well, now I can come over here and say, okay, this is 1. And number 4, we said before was 2, so this is 2. We're returning the result, whatever this is multiplied by, because I should have put this, that we're setting number 4 equal to the product of these two. So 2 times 1 is 2. We put that up here for number 4. Number 3 originally was 3. 2 times 3 is now 6. And then we come here, times 4. 4 times 6 is 24. and then number 5 becomes 120. Does that make sense?
Can you repeat that?
Sorry, it's confusing. Yeah.
Yeah, I was just gonna say, one way that I like to think about recursion is it's kind of like, I don't know if you guys have seen the movie Inception, like the concept is a dream within a dream within a dream. It's the same thing, but it's with the function. And so you always have an exit condition. So that first if statement, if number equals 1, return 1, that's the exit condition. And then there will be another return that automatically happens if the exit condition can't be met. And that one, that return statement calls the same function again. And it keeps checking every time. And it's like you're going inside another iteration of the function every time until the exit condition is met. And then when that happens, it completes that condition, and you kind of complete each iteration of the function up through the layers until you're done with the initial one.
Yeah.
I
That
don't know if
was.
that makes sense.
So how do you know that it's an exit function? How do you know that the return method is the exit?
So like here, we see that we're not returning something that calls itself. So like this, we're continuing to call factorial recursion within itself. If you see that, that's not going to be the exit function. If you see just like return 1 here, it's not calling itself, and so that's going to be the exit function. You can have different, you can have like different return values for, like, you don't just have to have one place where you're calling it's calling itself. There could be different conditions where you say, okay, I'm going to call it with this number instead of this number, and you can have different things like that in there.
This is a little bit redundant because I think you explained this already, but compared to Inception, this goes all the way down to the bottom layer, and then as it comes out, it runs the actual function. Like, like all the multiplication stuff doesn't happen until you reach
Yeah.
the exit.
So like here, where it's like number times, it waits for this function to return something before it actually does the multiplication.
And it won't return something until the exit clauses.
Yep. So this is dangerous if the exit condition never happens, then it's just going to keep going and calling itself. So that's dangerous there, but if you've structured it well and you're making your algorithm correctly, then you'll be okay. Did you have one?
That was
Okay. Okay.
So say, for example, with this one, if you were to pass it a negative number, it would be stuck in a row because it's subtracting.
Yeah, it's never going to get to 1. That's a really good example. So like, obviously this is flawed because I don't even know if mathematically how you're supposed to do function or do negative factorials. Which do you think would be faster, the recursive or the iterative method? Who said that? So I think in this case, you'd actually find that the iterative one is going to be faster. And the reason being is, although this is actually a little bit less code that you're writing here, your iterative function doesn't have the overhead of calling another function and adding to the callback stack. So yes, recursive is great, but there are places for iterative and there are places for recursive. You need to know both. And I think that you, especially if you want to get into development, you need to know both, and you need to have practice with this kind of stuff so that when you see a problem that is going to be better suited for something recursive, that you do the recursive function rather than trying to do it iteratively. So we're going to talk about trees in a little bit, and I'll kind of explain how that might be that's a much better use of using recursion than if you're trying to do something iterative. Let me put this down. Okay, let's just talk about some of the key differences then unless anyone has any other questions. A condition, and we kind of talked about these, but a condition statement decides the termination of recursion, while a control variable's value decides the termination of an iteration statement. So, like in our example, with this for, the condition that's being met is just that we keep going through this until I basically is equal or less than 0. And then we stop. So the condition being met is not dependent on what the result is. It's they're kind of separate there. Versus with this recursive one, it is going to be dependent on what we pass in for number. So that's kind of the difference here. One of the differences is that like the conditional statement is the conditional statement here is what actually terminates the loop of going through and continuing to call itself, versus here it's just, did we reach 0? Infinite recursion can lead to system crashes, while infinite iteration consumes CPU cycles. So even though they're both infinite, they both end up doing something a little bit different. Don't ask me how that all works, because I don't know. But just know that they're a little bit different. Recursion repeatedly invokes the mechanism and constantly the overhead, kind of like talked about, of method calls. You're going to have this stack of just the same thing. That is something else that your system has to process, rather than just going through a for loop. It can be expensive. Like I said before, recursion, the code a lot of times is going to be smaller. You're not going to have as much code there, but and iterations will make it longer, like we see right here. However, that doesn't mean that it's going to be faster necessarily. Less code doesn't mean that it's faster.
So which one is faster? We go back to the answer that it depends.
So with this example, it's going to be a little bit more difficult, because with that, I was talking about, it still depends. With that, I was talking about like which data structure you should use. Here, which one you should use, it's also going to depend on what you're doing. Like I said, I think that this one is going to be faster if we did start and stop, just because this one has the overhead of function calls. However, if you, like in a tree that we're going to talk about in just a minute, if you're trying to find a specific node in a tree, you don't know how big, and if you don't know how big the tree is, or you don't know where to go, something recursive is going to be a lot better, because you can keep calling yourself until a condition is met, rather than giving it an exact, like, here's how many times I need you to do something, because you might not know that. And there's another, I have like another problem that we'll kind of talk through about, how could we solve this? Actually, that might be coming up. Okay. Any other thing about recursion? I'm sorry I'm not doing very much hands-on code right now, but this is something that we only have like half an hour left, and this is much more just, let me explain the concept, get you exposed to it, and I kind of will leave it up to you guys more to become experts in these things. Okay, so let's talk about some trees. So here's a really basic diagram or image of just what a tree kind of looks like. A tree is another kind of data structure. Not all, you're usually not going to find like an implementation or a class of trees like we find in C# with queues and stacks and everything. Trees are a little bit more abstract, because it's like a conceptual mapping of how these things are related to each other. And so you can implement trees in a variety of ways. One we'll see is like a sorted array. You can actually show the same kind of data, or like store the same kind of data in your system, but using a sorted array. And so they're a little bit more abstract and complex than some of these other data structures that we've looked at, but they're really, really useful. Especially like we're going to talk about binary search tree, searching and stuff like that. So Let's go ahead and talk about these. So with a tree, each of these circles are nodes. So like we talked about before, linked lists, or linked list and double linked list, they all have nodes. Trees also have nodes. The node is going to store data, and it may or may not have a child node, or be pointing to a child node. In some cases, you're going to be pointing to two children. Like in A has a child node B, and A has a child node C. Or sometimes we call them a left and right child. We can look and we can see that in somewhere like this, D, H, and I, this is actually a subtree. If you were to get rid of, or like just cover up everything else, you would see that that's its own little tree. So within each, within a tree, you have subtrees basically for each node. If we see a node that doesn't have a child, we call that a leaf node. Okay. Let me look. We have a whole bunch of definitions. So we have node, root. That's just the topmost node in the tree. So that's kind of like your entry point to it. An edge is the link between two nodes. So, do you have a question or just, okay? So these lines in between each node, those would be edges. A child, kind of self-explanatory there. It's like, so C is a child of A is a parent of C. I think that you can see that visually right here. Leaf, like I said, node that doesn't have a child node. The height is the length of the longest path to a leaf. So if we start at the root and we go down the tree, you can go like B, E, J. And that was 1, 2, 3. So our height would be 3 because that's how long the longest path is to get from the root to another node. And then our depth that's specific to each node. So if we look at B, we would say that B is at level 1, and that's its depth. If we look at D, it's at level 2, and that's its depth. Okay. Visually, is this making sense right now? Okay. Okay. Yeah, you guys say genealogy. That's actually a really good example of this. That's why we call it family tree, right? They're the same kind of structure. Okay, what do we have? Let's go ahead and look at a visualization. So all the visualizations kind of suck for these, but I found 2 that are kind of cool. So let's just make a random tree. It went ahead and made it for us, and if we want to insert a value. Now, the way that like a tree will work here, and I believe, yeah, this is a binary search tree. We'll get to those in a minute. But a binary search tree, everything on a node's left has to be less than it, and everything on a node's right has to be more than it. And what I'm talking about is the values that we see. So if we see 56 here, if we go to its left, so like left child, we see that it has 48. That's because 48 is less than 56. If we look at 48, on its right, we have 50, and on its left, we have 40. 50 is less than 48, but it's also less than 56. So let's watch something get inserted. What should we insert? Maybe like 54. Let's do that. So if we put this in, it starts at the top. It says, 54 is less than 56. It's greater than 48, and it's greater than 50. So it traverses the tree to put it in at the correct spot. This is something where recursion would be really useful, because you start at one place and you say, hey, is your left node or your right, like, am I greater, is the thing that's coming in, is it greater or less than that root node's value? If it's less, it's going to go down the left, and it's going to call some insertion function, like repeatedly call itself until it finds where it fits. You can't really do that with a for loop when you don't know how far it's gonna need to go, because you're just gonna need to use it's gonna be a lot quicker to use recursive stuff. So let's say
Can you search in that recursion?
yeah. So if we find if we do find values, so say we want to find the 79 over here. So it starts at the top. It says, oh, 79 is bigger than 56. It's bigger than 69, less than 83. There it is. So it makes searching really, really easy, and we'll go over some searching stuff with these two.
So, wait, never mind, answer my question.
Okay. How's everyone feeling with this right now? I'm not going super into depth with these, but
You only have 2 child nodes.
yeah, in a binary search tree, you can only have 2.
But
Yeah.
What happens if it comes with the same value as?
I think that we'll just say you can't do that. So let's try 50. Oh, this one lets you have it. I don't like that. Huh?
If you did 50 again, since that's the bottom one there, so they end up kind of you know what I mean? Oh, so if it's equal.
It's less triangle too, it keeps going down.
Well, because even 50, went into 50.
I don't think that it would normally do that. I didn't make this, so and if anyone else has anyone else had any background with it?
I don't think you typically allow read these.
Yeah, that just doesn't make sense. So maybe I'll show another visualization here. Let me pull up this one. Whatever. So what I kind of like about this one is it'll kind of tell what's going on. So let's here we'll put 2 of them in. So over here it tells you what it's actually doing recursively. So it just keeps calling this function that just says that this is pseudocode for what it's doing. If it's found, then create the new vertex. If it's not found, if the value to be inserted is less than whatever it's on currently, go left. Else go right. So that's a perfect example of how this does it recursively. And let's just do that one more time. Let's do 29. So we look here, the value's less, else go right, go left, and then we see that it puts it incorrectly. It's still going left. But it just keeps calling that function that has that is doing those things.
What happens if we insert the number that's already inserted into this one?
Let's see. Let's just do 5. Go. No duplicate vertex allowed, so they don't even let you do it. If we want to remove something, let's remove 38, because I think this is also interesting. Because this has a parent node or has a child node, so what's going to happen here? It's going to go find 38, but then it also has to go to its child nodes and say, hey, you need to get connected to 44. Let's insert 33 and see what happens. And then remove 32. Actually, let's do 35 and 33. Okay, so now let's see what happens when we get rid of 32. So this is interesting because 32 now has 2 child nodes, so how will it know which one to make the new place there? And it chooses 33. So there's a lot that you do with, there's a lot of different functionality that you can have with trees. You can also do like an in-order traversal. So we look at the root, and then you can even see like it's doing in-order left. It's calling itself there. And so it's with traversing, it just means that we're going to go through each node in the tree. And it looks like it's going from left to right. So it started at the root, went all the way to the left, and then now it's going to the right. It should go all the way to the left that it can now. So it'll keep going down to 30, down to 29. It'll go back up all the way to 33. Make sure that we finish off 33, or 33's child nodes. Go back up all the way to 44 and go back down that right side. Yep. And this is all done with recursion. You can see here that it's calling the exact same function over and over again, just by what's happening right there.
Do you know how, because there's a term, I think it's like a complete search tree, meaning like every layer is full until you get to the bottom. Is that something that we need to know as well?
I actually have that right here. I don't have complete. I had complete, and then it was funky. But I think full and balanced are important to know. So binary, I'll just go over this and then we can talk about that. So binary tree, that's what we've been kind of looking at. Those were specifically binary search trees, which we'll talk about in just a sec. A binary tree, the node will have a value, a left child, and a right child. The left and right child are just pointing to the nodes that are its left and right children. A binary tree does not need to be sorted. A binary search tree will need to be sorted. So what we've been seeing, how it's been placing things, that has been the reason it's doing that so that it's sorting it correctly is because those were binary search trees. A full binary tree is where every node has either 0 or 2 children. So, for example, this would not be full. The reason being is E only has 1 child. If it had another child or it did not have any children at all, it could be full. A balanced binary tree is when the left and right subtrees of every node differ in height by no more than 1. And this is just saying that we're basically getting to a minimal depth height for the whole tree while also trying to keep it as full as possible. Okay. With complete, can we just talk after about complete?
Yeah.
Okay. Again, I'm not an expert in all this stuff, but I hope that you guys are learning something and at least can take away from this to go and learn more. Searching through a tree really quickly, there's 2 different kinds of search. You can do a depth first search and a breadth first search. And I have 2 little like animations to kind of show what's going on here. So with a depth search, we're looking for n. Breadth first. So the breadth first, it just goes across each level until it can find n. So if we see here, it's showing us how many steps. It's going it did level 1, 2, and now it's on the last one. This takes 14 steps to find this particular node in the tree. With a depth first, it goes down first and to the left all the way and kind of looks through each subtree until it can find n. So it goes down to the left first and then the right. You can also have it go and start from the right and then go to the left. But this is kind of these are 2 common ways of searching a tree to find a specific node or value in it. I don't want to show the code for all this. That's just, I think the concept is more important right now. And if you can look it up later, awesome. And I have a whole bunch of resources at the end, like interview prep resources and like where I got all this stuff from. So binary search tree, sometimes called an ordered or sorted binary tree, and it keeps its values in sorted order so that lookup and other operations can use the principle of binary search. Yeah. So an important part of this is that the value the value of a binary search tree's node is larger than the value of the offspring of its left child, but smaller than the offspring of its right child. So, yeah, actually this is a great example. So if we're inserting into this, we can see that everything with 21 as the root, it's going to put everything that's greater than 21 to the right of it, and everything that's less than 21 to the left of it. And this is another example of that recursion, and it's exactly what we saw with those visualizations of where it's the same function that's calling itself over and over again to make sure that it is going to be less than or greater than that particular node for whether it goes to the left or the right. Okay. Okay. So let's just talk about the searching example, kind of talk it through. I want to know if you guys have any ideas, and then I'll kind of show you something that is kind of interesting. So say that you had a sorted array of 10,000 numbers that ranged from 0 to 100,000. What's the most efficient method to get the index of a given number x? Anyone have any ideas on how you could do this? Like, it doesn't have to be recursion, but like, what are some, or it could be iterative.
You pick the number in the middle and it says greater than, less than, and you keep going like that.
Okay, that is one way to do it. Any other ideas? Okay, let's talk about that in just a sec. An iterative way to do this would be, say, you just do you go through and you just do a for loop, and you say, for all the numbers in this, just keep going through until I find x. If I find it, get out of the loop, I return x, that's great. Problem is, what happens if x is like the 9,000th element? You've just gone through 9,000 elements just to find this one. What he gave an example of is a great example of what you could use recursion for, where you say, okay, I'm going to find half of this array, and I'm going to say, because it's sorted, I can say, if x is less than this value at halfway through, then I'm going to look at everything that's greater than the middle, or half. And you can keep going through that until you can find that specific element. But each time you cut down, you're making you're getting way more efficient because you don't have to go through all those elements. Now, sorry, go ahead.
I was just gonna say, couldn't you also like subdivide the array to start with, and then have multiple recursions happening at the same time in different areas?
Yeah. The only thing is, because it's a sorted array, you don't really need that to have, like, if I know that it's greater than halfway through, then I don't need to do anything less than that. What was I going to say about this? So, but I mean, like, you're going to miss out, say it's the 10th element in your list, or in your array. It would be way faster just to use iteration, to do a for loop, find that element, because you only have to go through 10 things, whereas if you start with half and you're like, oh, the 10th element is less than the 5,000th element, then you go down to the 20, like, you cut that in half and you keep cutting it in half. That's probably going to take more time than just doing a for loop, but on average, it's probably going to take less time to create a recursive function that goes through it. So that anything that you give it, like whether it's something that, maybe your iterations have to go through like 1,000 elements, but if your recursive function only has to go through 500, that's going to be better. So what's great about this is conceptualizing it as a binary search tree. So this is great because what we have is we have a sorted array at the bottom, and then we also have our binary search tree. So the sorted array, they're just doing iteratively, going through and looking for the number 27. And so they're starting at the beginning and going through it. And it would take 10 steps to get to 27. Here, with this balanced binary search tree, it starts at 21, goes to 28, 25, 27. And that's all it took to get there. It took 3 steps, while going iteratively, it would have taken 27. Now, say that the number that we were looking for was, say it was 5, okay? It would be way faster to do it on the sorted array. But it's also only going to take like 2 extra steps longer to do it in this binary search tree. So in reality, you're probably going to be averaging about probably better if you're using, as far as complexity goes, if you're using the search tree rather than just a sorted array and iterating through it. So I'm talking a whole lot, but I hope this is valuable.
So when we said one way we could do it is splitting it in half over and over and over, we can do that because it's in a binary tree structure, or are you saying that's another way to do it?
So the trees are more of a way to visualize how you're doing things, because if you want to implement a tree, you'd have to probably write it yourself and write the implementation. But another way that you could look at this is what they're doing is they're just starting at the middle and they're going to half and they're going to half and then they're going here. So you could do it just with an array, but visually it makes way more sense to look at it as a tree. And this is conceptually what's happening. So something that might help is tree to array and back again. So here, we'll wait for it to restart. They're taking a binary search tree and they're degrading it all the way into a sorted array. So they're saying that this array can actually look, or this search tree can look, binary search tree can look like an array. Here they're doing the opposite. They're taking a sorted array and turning it into a binary search tree. So I think this is a really good visualization for the concept of a tree. Doesn't have to just like in the code actually look like a tree. You can have it be a sorted array and be just as efficient as if you had went out and created a whole entire tree.
So you could have an object that's an array, but you would just kind of treat it like a tree in the way that you search on it?
Yeah.
Okay.
And you just write recursive functionality for that. For people who know about binary trees and stuff and recursion, is that kind of good there? Okay. I'm not leading you astray here. Okay, once again, this is just like a brief overview of what you can do with it. Let's talk a little bit about Big O notation. I found this really good video where some guy just talks about it in 5 minutes. So let's just take the last little bit, look at some Big O stuff. Who's heard of Big O before? Okay. So Big O is basically like you're talking about how efficient your program runs. And it can be both in time and space complexity.
Notation. So
Just a sec. You guys know which one it is?
Oh, what is it? Big O notation is an analysis of an algorithm's efficiency. We cover a lot of algorithms on this channel, compare them, and some idea of how long they'll take to run. Big O gives us an algorithm's complexity in terms of the input size, n. It gives us a way to abstract the efficiency of our algorithms, or code, as they run them. We don't care about the stats of the machine. Rather, we examine basic computer steps of the code. We can use Big O to analyze both time and space. There, look at efficiency. We can examine worst case, best case, and average case. When we're talking Big O notation, we typically look at worst case. This isn't to say the others are unimportant, however. Let's talk about a few rules. First, Big O notation ignores constants. For example, if you have a function that has a running time of 5n, we say that it runs on the order of Big O of n.
So this is the
as n gets large, the 5 no longer matter.
This is the kind of the notation that they normally will do. They'll have O and then n, or log n, or whatever. And this is and we'll see a chart that talks about like this is how good that actually is.
In the same way as n grows, certain terms dominate others. Here's a list, but I'll show you a visual on the next page.
Here we go.
We ignore or drop low when they're dominated by.
So typically, like, this is kind of the order of like, this is going to be fastest and this is going to be slowest, basically. Where if it's 01, then it's just going to be execute, no problem. Like ON would be, this would be like a for loop, and he'll show this in just a sec, where you have to go through n number of iterations to execute that code. Yeah.
High order ones. Take a minute and study this chart. It can be found on bigocheatsheet.com, along with a handy guide on the Big O of various important algorithms.
So you want your algorithms to stay in this range if you can. Like,
Let's run a few
you really don't
examples so you can
want
see what I mean
this
by basic
because
computer steps.
this is going to be really slow.
We'll start with constant. Imagine
I don't
you're in
like
the
that
following
sound.
line of code. This basic computer statement computes x, and note it does not depend on the input in any way. We say this is big O of 1, or constant time. What happens when we have a sequence of statements? Notice that all these are constant time. How do we compute big O for this block of code? We add each of their times, and we get 3 multiplied by big O of 1. But remember, we drop constants, so it's still big O. Let's look at linear time. Suppose we have the following for loop that prints the numbers 0 to n. You know the print statement is big O of 1. This means the block of code is n times big O of 1. In other words, big O of n.
So really quick, the reason being is because we have to go through this n times, right? So even though this just is big O of 1, because we're doing it for however much n is, that's why we're saying that it's n times big O of 1.
Here's another sequence. First line we know, again, is big O of 1, and the for loop is big O of n. The total time is the summation of these two, but remember we drop low order terms. When n gets large, the time it takes to compute y is meaningless, as the for loop dominates them. Finally, let's look at quadratic time. I think you can see that the print statement will be executed n times n, which gives us big O of n squared. Let's do 2 more examples covering everything we've talked about.
I don't know why the audio keeps cutting out.
What is its total runtime? Well, we know the of these, so the total runtime is simply the max of the 3. The nested for loop dominates here, so we get big O of n squared. How about this statement? Pretend the sequence of statements in each clause have already been deduced to the big O as shown. I talked earlier that when we're discussing big O, we usually look at worst case scenario. So for this situation, we choose the largest runtime, which happens to be big O of n squared. Gives you an understanding of big O notation. Let's wrap up by talking about the real world. When you're coding your algorithm, please realize that constants absolutely do matter. A lot of situations have small input sizes, so a constant of 2 or 3 could have a lot. Lastly, for the same reason, be cognizant of best and average case. Application, this may be more applicable for your algorithm. As always, thank you for watching.
Okay, so I hope that you guys got out of that, like, if you're in I've had a bunch of interviews where they say, hey, so you wrote this, you did this whiteboard problem or whatever, what's the big O? what, like, how efficient is this? Or they might not even say the big O. They may say, what's the complexity? How efficient is this? And what they're really looking for is what's the big O. And so you need to say like, oh, if I used 2 for loops, that's going to be n squared because you have to go through like that whole list twice. Or if you're just using 1 for loop, it's big O of n. If you're using different data structures or you've created your algorithm different ways, it'll end up being different complexities. I'm not going to get into that, but go look it up. And I have more resources for you to see. So this is kind of the stuff that we've seen on that you can see on the Big O cheat sheet. Here's like basically how good it is if you have with different levels of Big O, I guess. You can see here what, like for an array, accessing it is Big O of 1 because it goes directly to that element that it needs to find. With searching it, it has to go through, like the worst case is going to go through every single one, right? Average is also the same. So we can see, you can come here and see like, oh, what are the different cases? Sorting is also going to be, people will ask about, how efficient is this sort for your algorithms. Once again, it's mostly about complexity and how efficient your algorithms really are. Any questions about Big O? Okay. So I just have some resources at the end. Again, you can go to this site and look through it. There's some really good ones. There's a whole course on data structures on Udemy. Also some interview prep stuff. There's this really cool, someone made this tech interview handbook where you can just go, it's on GitHub and you can go through and like do a ton of stuff. They have all your, they have a whole bunch of different data structures and algorithms. They have things to help for interviews. I really hope this was helpful. I hope you guys have learned some things about, some more about data structures, and yeah, thanks.